Welcome back. And the last 2 weeks, we are going to deal with an introduction to Green's functions. Now, Green's functions are very much used, in particular in solid state physics, in particle physics, and also non-relativistic quantum mechanics. They tend, however, to be a little bit more involved when it comes to the solution, because as you will see, we are going to have to deal with the poles in the energy propagators, which often complicates the implementation of the many-body machinery. However, a Green's function, and through quantities like spectral functions, etc., we have a complete information about the system. So Green's functions are very powerful, but in order to get there, we need to remind ourselves of some of the ingredients from many-body perturbation theory, because at the end, even if the Green's functions, we can sum specific terms to infinite order, we end up doing a perturbative expansion anyway. So what I wanted to do now is to repeat a little bit about the time dependence and the way we treat time. This leads also to something which is called the adiabatic hypothesis, which some of you may have heard about. And then if we get time today, we will get into Green's functions. It means also that we need to think a little bit about the time ordering. And that leads to another technicalities. So there is a bunch of technicalities today. And one of these technicalities is what is called the time-dependent Wick's theorem. So which is an extension of the time-independent Wick's theorem. Because when we now deal with time dependence, we have to think about causality. So these are some technicalities which are coming up. And then we are going to move into Green's functions in more detail tomorrow, and also Dyson's equations. But let's see how far we get. So I wanted to repeat a little bit about these definitions of pictures. Like, yes, last week we discussed the Schrödinger picture, we discussed the Heisenberg picture, and we discussed the so-called interaction picture. Because that lends also to a redefinition of creation and annihilation operators in terms of time-dependent creation and annihilation operators. And for those of you who have taken a course in field theory, you've probably seen the quantization of the electromagnetic field or the quantization of fermion fields. And then you probably encountered the way you deal with the time dependence. So this means a change of the creation and annihilation operators. And that leads also to a slight revision of Wick's theorem. Let me quickly remind you a little bit of the material which we discussed last week. So let me just bring that up. And we had a set of slides. And let me bring this up in a full screen mode. So what we did last week was to look at these different pictures. So I just wanted to quickly remind you of some of these technicalities. So if you look at Schrödinger's equation in its full glory here, this is something which, if we assume that the Hamiltonian is time independent. So just keep that in mind. This is a basic assumption which we are making now. And we can then solve this one by rewriting that, we just integrate up. So we would have a Hamiltonian which acts at a time t and a time t0. So we would start integrating from t0 up to time t. And this would be typically the solution at a time when we can, for instance, solve the problem. So when we are going to introduce this adiabatic hypothesis later today, we are then going to assume that at t0 equal to minus infinity, the system is not interacting. And then we know the solution. It could be a Slater determinant. It could be a permanent if we're dealing with bosons, which would be the wave functions for symmetric types of particles which obey the symmetries of the bosons. And then we can evolve this. So this exponential here represents a unitary transformation. And you can quickly see that this is a unitary transformation. If you take the Hermitian conjugate of this one and multiply it with itself, this is going to give you the unit matrix. And then what we did was to introduce a new definition of the wave function in the so-called interaction picture, and that is given by a new unitary transformation, where we simply have the unperturbed piece, and that acts on the Schrödinger picture wave function. And when we did these types of manipulations, we could then find the equation of motion here when we take the time derivative, and that led to an equation of motion which looks like this, where we now have redefined the Hamiltonian, so that the Hamiltonian has an explicit time dependence through these unitary operations. But the original Hamiltonian which we had is time independent. So that's an assumption which we make. If we have a time dependent Hamiltonian in the original equations, then we have to be a little bit more careful. But the basic machinery is essentially the same. But like in the way we've been treating things in this course, we've essentially been looking at a time-independent Hamiltonian. And I guess for those of you who have taken a course like Physics 4110, Modern Quantum Mechanics, you've seen this in so-called pictures. And then you can calculate an expectation value or a transition probability if you go to a different state. And then you can actually calculate the transition probability for specific operators. If you go from the same state to the same state, you will have the expectation value of a specific operator in the different pictures. There is another picture, so I'm skipping some of these. These unitary transformations have a specific property, which we listed last time. And these properties deal with the unitarity of the operator. And clearly, when we have the same time, if you have in this quantity, if you have t equal to t prime, then this one is obviously equal to 1. And you can see that quickly from the definition. And you can solve these equations. And one of the quantities which we introduced then, when we manipulated the equations, is actually to obtain an equation of motion for the time. This operator, this unitary transformation, is also called the time evolution operator. So if you can solve this equation here, you basically solve the many-body problem. And this type of equation, as we discussed last time, can actually be rewritten. And if we just end up here, we can rewrite that in terms of something which now contains a set of time-ordered operators. So that means that the time t1 is larger than t2, larger than t3, etc. And we have a sequence of such operators. So if we now go to many-body perturbation theory, and we want to make the link here, which we will actually do a little bit later today, then we have to be a little bit careful with the way we define the Hamiltonian. And that's where this adiabatic hypothesis comes in. So this is the general expression for this unitary transformation. And if you now look at the terms here, this is going to represent the Hamiltonian to given orders. So if you have n equal to 1 here, this will have the wave or the unitary operator or the time evolution operator or the wave operator, as it's also called. So this quantity has different names, because if you go back a little bit to the equations here, you see now that the wave function which we want to have is now given by the evolution through this quantity here. And if you think back to what we did in time-independent perturbation theory, we had the unperturbed wave function plus a correlated operator or correlation operator, which then included all the higher order many-body terms. And this quantity here, this u, is going to play the same role as the correlation operator or the wave operator, as it's called. So you will see this being named in different ways. It's a unitary transformation. It's also called the wave operator or the wave propagator, etc., etc., etc. So there are many different names which are being used in the literature. But in principle, now as you have this term here, you can actually use this in a perturbative expansion, and I will try to show you how that pops up. Before we move on, there is another picture which is interesting for us, and this is the Heisenberg picture. And that's the one which is used when we are dealing with the Green's functions. So in a Green's function approach, we actually take another type of unitary transformation where we have the full Hamiltonian now acting on the wave function in the Schrödinger picture. And with that, you can then redefine all the operators. So this will be an H here, subscript H is now your operator in the Heisenberg picture. And then we also see that if we have a time-independent H, then we can actually, combining the Schrödinger equation, we can actually show that the time evolution of this guy here, the time derivative is equal to 0. So there are different simplifications with the different pictures. So just keep that in mind. And they're all related by a unitary transformation. And then we can calculate the different expectation values. We can set up the equation of motion for a specific operator, which in this particular case is given by a commutator between the operator and the Hamiltonian. And then we can, in a similar way, we can actually rewrite the a given operator in terms of this transformation here, which in turn implies that if we take time equals 0, this operator in the Schrödinger picture is given by these operators in the interaction picture and the Heisenberg picture, time equals 0. They are all equal. And the same with the wave functions at these different times when we take time t equals 0. And this has to do with the fact that the wave function in the Heisenberg picture is time independent. And then you can relate this with the time evolution operator, or the wave propagator as we call it, or just the unitary transformation in this specific way here. So they can be related through different mathematical relations. So what we are going to look at now is the adiabatic hypothesis, and I'm going to switch back to the whiteboard now, if that is okay. But before we look at the adiabatic hypothesis, I wanted to say something about the creation and annihilation operators in this new picture, the interaction picture or the Heisenberg picture. And then we also need to modify slightly Wick's theorem. And we are going to use these operators now in a time-dependent representation. And that means that we need to change a little bit the way we deal with the Wick's theorem, mainly because we don't want to break causality. So let's bring up the topics for today. And let me quickly remind you of some of these expressions which we have. And what we are going to do now is to look at the wave equation in the creation and annihilation operators in the interaction picture. So let's take a look at the creation and annihilation operators. Let me just rewrite that one. Creation and annihilation operators and annihilation. So this is just a technicality as an intermediate step towards where we want to end. So these are annihilation operators. With time. And this is going to lead to a modification of Wick's theorem as well. So let's now assume that we have the standard unperturbed Hamiltonian, which is given by a sum over given states k. So I'm not specifying the states. And this is now assumed, this basis k is assumed to be an eigenbasis of this operator H0. And this is given by an AK dagger of AK here. So these are just general states k with no specific reference to a given basis. But we're simply assuming that this basis is now a orthogonal basis and an eigenbasis of H0. So if we now go back and look at the definition of this operator in the interaction picture, what we have then, if we now look at that one, so let me quickly remind you of that expression. So an operator in that picture is given by E of I of H0 of t divided by h. And then I have the operator in the Schrödinger picture, and we're assuming that this is time independent. And then we have an E of minus I of H0 of t divided by h. By the way, no, I did put on the recording. I did that. Yeah. Okay, good. So my goldfish memory needs a reboot. And I needed to see if I had put on the recording here. Good. So with that one, if we use this equation here, then what we could find is an equation of motion. So let me just quickly repeat that. So the equation of motion for that specific operator in this picture is now given by the commutator of the operator in this picture here with H0. If I took the Heisenberg picture, it was the full Hamiltonian. So if I use that one, what I can do now is to look at the time-dependent operator for AK as a function of time t. So the operator in the interaction picture is now the annihilation operator, and then I can do the same thing with the creation operator. So what we have then is then an AK, and observe now that there is no time dependence here. So in this specific expressions, because what we are doing, sorry, I have the intermediate step, which I was a little bit quick here. So this is given by E of I of H0, and then I have T of H bar, and then I have the commutator AK of H0, and then I have E of minus I of H0 of T divided by H bar. So this is the expression which we have for the equation of motion. So the time dependence comes in here. So we have an explicit time dependence. And here we have no time dependence. Like that. Then, if I now look at the commutator, what I have, if we just remind ourselves about this commutator, so we have an AK dagger of H0, and that is given by AK, and then I have a sum over K prime, epsilon K prime of AK dagger AK prime, like that. And if we write it out, we can easily see, if we do the commutators now, we have a K, and then we have the epsilon K prime, and then we have AK of AK prime, and this is minus, and then I have a K prime, and then I have my AK prime, AK, multiplied with epsilon K prime. And when we do the math here, we get epsilon K times A of K. So the operator which we have then is now given, or the equation which we get is the equation of motion turns into an AK of T, and that's going to be given by an epsilon K, and then I have my E of I of H0 of T of H, and then I have my AK, and then I have my E of minus A of H of T divided by H bar. And this quantity here is nothing but the definition of an operator in the interaction picture. So in order to avoid a kind of excess of subscripts and superscripts, I'm skipping the I for the interaction picture, and I just keep T to indicate that this is a time-dependent operator. So this is nothing but the definition of the operator in the interaction picture, but I skip the subscript I in order to avoid, a confusion with all these kind of possible subscripts, etc., etc. So what I have then, if I now look at these operations here, if I then integrate up, and this is an equation which is pretty easy to integrate. because it's just epsilon k times ak of t. So that gives me an exponential. So what I have then is that ak of t, and then I have ak at time t equals 0, and then e of minus I of epsilon k of times t divided by h. So you can find a similar representation if we repeat this exercise. So similarly, what we have is an ak dagger of t, which is now given by an ak dagger, the original one, time independent quantity. And then this is given by I of epsilon k of t divided by h bar. So particle states are distinguished by whole states later by a minus sign in front of the exponential argument, the argument to the exponential function. And I guess this is something which some of you may have seen before. So what becomes important for us now is actually to look at the typical. Yeah, go ahead, Joseph. You have a question.
The last step, it's, can you unplay more when you pass the AQ to? It's an operator. It's possible because H0 and H0 is operator too, no?
So when I take t equals 0, when I integrate up, is the integration which you have problems with? Is that the case?
Yes.
So because what I'm having now, when I integrate from time t equals 0 to time t, then at time t equal to 0, then all the operators in the Heisenberg pictures, in the Schrödinger picture, and in the interaction picture, they are the same. Because at t equals 0, then when I set in the limit of t equals 0, then this ak is actually equal to ak of t equals 0 is equal to ak, the time independent creation and annihilation operator. And if you look, so let me just try to bring back the slides, and perhaps that may help a little bit. So let me bring back the slides here. So if we go back to the operators in the Schrödinger picture and the Heisenberg picture, so what we have is a equation of motion where everything now is given by this commutator where we have the time-dependent piece. So essentially what we have is the operator in the Schrödinger picture, which is ak in this case. And then we have ak here, and this is what I did. So I have these expressions which you have here. So ak is just it's the operator in the Schrödinger picture, which corresponds to the same expression when we now look at the link between operators in the Schrödinger, Heisenberg, and interaction picture at time t0. They're all given by the same expression. So if you then have the annihilation and creation operator instead of O here at time t equals 0, then they are all the same. And when I integrate up, then I know the limit at the time t equals 0, the result at time equals 0, and then I have to simply integrate up to time equal t. And then that gives me, when I integrate up, then the equations which you then see on the slides here. So the expression which you get then is the one which you see when I integrate up now. I get this expression here. So I just use the definition of the operator and interaction picture, and then simply use the fact that I integrate from time t equals 0 up to a given time t, and then I simply have this ak dependence here. I hope that helps a little bit in the explanation here. So let's take a look at now at an expectation value. So we need now to modify a little bit Wick's theorem for time-dependent operators. So let's take a look now at a vacuum to vacuum expectation value, where I now have a state, a k here, and then at the time t1, and then I have an ak prime dagger at the time t2. So if I'm plugging in the expressions here, what I would get then is an e to the minus I divided by h bar. And then I have a state now where I have to have a t1 minus a t2. I'm just setting in the expressions for the operators. And since I have a Kronecker delta, this means that I'm going to get an epsilon k here. And this is multiplied with 0 of ak and ak prime dagger. And in principle, this is now multiplied with a delta k of k prime. So I just plugged in the energy when k is equal to k prime here. So it could be tempting to actually set it up like this. So this will be an expression which now ends up being equal to e of minus I of divided by h bar multiplied with t1 minus t2 multiplied with epsilon k of delta k prime. Now, if you look at this expression here, do we have to think a little bit more, or does it look okay? So there's a small hint here. What if T2 is larger than T1? And what about T2 equal to T1 and T1 larger than T2? Which one of those, or which one of these makes sense to you?
T1 equals T2 is essentially what it is bigger now, so
yeah.
Yeah.
So if you look at this one, this breaks causality because T2 is larger than T1, so you cannot create a particle at a time T2, which is larger than T1, and then destroy it. That doesn't make sense, right? So this expression which you see here, this one actually breaks causality. When T2 is equal to T1, then we're just back to what we had previously. So that's also, you could then think of an instantaneous interaction. But since we want to bring in time here, the T2 equal T1 case is less interesting. The interesting case is actually the T1 larger than T2, because we create a particle at T2. So this breaks causality. Because if we have T1 less than T2, that means that we destroy or annihilate a particle, annihilate a particle before we have created it, before it has been created. So that doesn't make sense. So this leads to a change of Wick's theorem. So in order to keep causality or to respect causality, then we need to make a change into the Wick's theorem. So in order to respect causality, we need to modify Wick's theorem. We need to modify to its time-dependent version, to its time-dependent. And the proof is actually pretty similar to the one which we had for the time-independent one. So if we now look at a time-ordered set of the operators, so suppose we take an example. We now want to have a time-ordered sequence of operators. So we have an A1, of T1, and then we have an A2 of T2, and then we have an A3 dagger of T3, and then we have an A4 of T4. And the assumption which we have made now is that the T1 is larger than T2, and this is equal to T4, which is larger than T3. So if we now look at the way we would have this one, this would then be given by a minus A1 of T1, and then we have an A2 at T2, and now we're just referring this to the true vacuum. We are not looking at the modified vacuum with particles and holes. So we would have an A4 of T4, and then we would have an A3 of T3. So this sequence is actually okay, because now we would create a particle at the T3, which is a time which is smaller than T4 or before T4. And this would be the change of the operator. So we would have a minus sign because we need to change the two operators here. So what we can do then, if we look at that matrix cell, the example we had previously, so if we now look at the previous example, what we could say now when we have two operators, with two operators only, then we can now write out a vacuum-to-vacuum expectation value where T stands for time ordering. And then I have an operator AK of T1 and AK prime of T2. So this is now the time-ordered expectation value. And this is going to be equal, this specific expectation value, this will be equal to the following expression. So I'm going to have 0 of AK of T1 of AK prime of T2 dagger of 0, which is again equal to E of I divided by H. And then I have a T1, so there's a minus sign here, T1 minus T2 multiplied with epsilon K, and then a delta K of K prime. And this is the if T1 is larger or equal than T2. And then it's going to have a minus sign because now we are looking at the time order product. So we would then have a minus sign, and then we would have an A of K prime of T2 of A of K of T1 of 0. And that is clearly, with a true vacuum, this has to be equal to 0. And this is if T1 is less than T2. So this is the way we would define a time-ordered expectation value, which respects causality. So if I now go back to the expression you see here, so this time-ordered product of the operators has now to be modified a little bit so that we can have a set of operations which allow us now to respect causality. So when we now interchange the operators, so this will be an AK T1, because T1 is a time before T2. So that operation has to take place before we operate with AK dagger of T2. Does that sound reasonable? So these are just definitions which we are setting up so that we have some specific rules which we can use then. So what we want now is actually to rephrase this expectation value in terms of a time order product. So what we are going to introduce now is the time-dependent Wick's theorem. And it's natural then to remind ourselves of the normal product. So you remember now, if we had a chain of operators, which was normal ordered, suppose now we have a chain of operators like A1 at the time T1, A2 at the time T2, and then an A3 at a time T3 dagger, and A4 at a time T4, like that. Then this one would be equal to minus 1 to the power of 2, because I'm modifying this operator. So what you have here does not need to be a time order product. Okay, this is just the plain normal ordering which we used before. And then we have an A1 of T1. If we just use what we had in the time independent Wick's theorem, this is the way we could set this up. And this is independent of the time sequence which we have. And that means that it's necessary now actually to compensate for the time sequence which we have introduced. And so that means that when I take an operator like if I look at a contraction now between two operators of a T1 and an operator V, and now I'm just letting these be generic operators, this is something now which I would redefine as the time order product of U of T1, of V of T2, minus the normal ordered product of U of T1 multiplied with V of T2. So this is now going to be my new definition of the contraction. So let's look at an example again. So let's look at the contraction of an AK at T1 and AK prime dagger at a time T2. And this is a contraction. This is the same as my vacuum to vacuum expectation value of that quantity. And we know that when I do the algebra here, what I'm going to get is an E of minus I H bar. And this is going to have now an epsilon K of T1 minus an epsilon K prime of T2. So now I'm not plugging in the Kronecker deltas. And then I would have an A of K prime dagger, plus an A of K prime dagger and AK. And we know that this last quantity which we have here, this quantity here, that just gives us what we have seen before. That gives us a Kronecker delta of K and K prime. And this is the case for T1 larger than T2. Okay, so what you see now is what I've done here is simply to bring back the same definitions which we had before. So let me just quickly remind you of what we had before. So before we had AK of AK prime. When we looked at that one, that was given by an AK. We had the vacuum value, AK of AK dagger of 0. And then I have plus the normal order product of the two operators, AK of AK dagger. This is what we had before we plugged in time dependence. And this is now something which ended up with giving us delta K prime minus, and then I would have the expectation value of AK prime of AK of 0, and that last quantity was equal to 0. Okay, so this is what we did before. So what we are going to do now is to introduce the reordering of the operator, where we have T minus this normal order product. And if I do that, you see now that I get a plus instead of a minus, because I'm changing the order of the operators, AK prime dagger, and multiply with AK. And this equation which you have here is nothing but the one which leads to the anti-commutation rules with the Kronecker delta. And this applies for the case with the T1 is larger or equal than T2. So we should say T1 larger equal than T2. Now, if I then take the case for T2 larger than T1, what I'm getting then is the following. So I have an AK of T1 an AK prime dagger of T2 here, which is then equal to minus, and I have an AK dagger because I'm time ordering it, and I have assumed now that T2 is larger than T1. So this is my time ordering piece. And then I have an AK of T1, like that. And plus, and then I get an A because I have minus, and then I interchange the operator. So I have an AK dagger with a primed K and AK here of T1. And we know that these ones, when I now take the expectation values here, if I'm now going to put a contraction on it, this is the same as us taking the expectation values from vacuum to vacuum. And we know that in this specific case, we have an annihilation operator acting on the vacuum state, gives us 0. And here we also have an annihilation operator acting on the vacuum state, which also gives us 0. So this is equal to 0 in case T2 is larger than T1. So we are not breaking causality in that specific case. So what we end up with then is actually a modified Wick's theorem, where we now have as a goal to try to reorder everything in terms of normal order products. So the new Wick's theorem, when we have a sequence of operators with a U of T1 and a V of T2, etc., up to an operator C of a Tn here, the time dependent Wick theorem is now simply going to have the normal product of all these operators as before. It's going to have the sum over all the contractions over one pair of operators. So I'm just indicating that like this. I have the sum over all possible 2 pairs of annihilation and creation operators, still normal order. And this is going to be given by this symbol here that I'm contracting 2 pairs of creation and annihilation operators. And this continues all the way up to the contraction of all pairs of operators. So this would be an N, and then it has all possible contractions, etc. here. So this would be all the possible contractions which we can set up. And if we look at the case with for 2 operators, which we had, this specific case which you saw here, this one, we have proven, or we have showed it for 2 operators. So at the end, we are just actually going to get the same type of expression which we had before. And the proof of the theorem, it follows much the same line as we did for the proof of the first theorem. So we need to have a lemma where we add an operator at the time t prime, and then we need to distinguish whether this operator is a creation operator or an annihilation operators. But the proof follows very much the same recipe as we had before. So that means that when we are calculating everything then, when we are looking at that, what we have is that the time ordered product of all these, or the time ordered expectation value, all these operators, Z of T of N, 0, is actually going to be given by the following. So I will have a sum over all the possible contractions of all pairs of creation and annihilation operators. So I will have a U of T1, a V of T2, up to a Z of Tn. And we are taking all possible contractions here, just indicated by this, if N is even. And obviously this is 0 if N is equal an odd number. So Wick's theorem for this time-ordered product of operators is going to take much the same form as we have seen before. And after the break, we are going to look at some further examples where we look at the sets of operators. And we're also going to introduce a more compact notation for these set of contractions, because that will give us something which is going to be very useful when we introduce Green's functions, because Green's functions will have time-dependent creation and annihilation operators. So the whole thing with the Green's function, which distinguishes us from what we did earlier, is that now we can explicitly bake in time. And time, when we are doing the calculations, is often Fourier transformed into energy. So we can rewrite the equations either as a function of time or as a function of the energy of the system. And for those of you who have taken a course in quantum field theory, you will see immediately the connection between what you did with the relativistic theory, because then you would have energy and momentum as the 4 possible degrees of freedom, or time and momentum, or time and position, and energy and momentum. Now, we can Fourier transform time into energy, and that would give us the non-relativistic equivalent of what you have seen in quantum field theory. So you can build up a totally parallel quantum field theory for non-relativistic quantum mechanics. And Green's function theory is actually in the non-relativistic case, and the propagators you obtain, etc., are the equivalents of what you see in quantum field theory. So for those of you who have taken a course in quantum field theory, much of what you see here can be used in the non-relativistic formalism as well. So what I'm going to do now is just to bring in some examples. And if we now go back to that case when T1 was larger than T2, we are just going to redefine a little bit the way we set it up, and we will also introduce the definition of the corresponding contractions when we are dealing with the whole states, so that we can then use what we have now not only for the true vacuum, but also for states below the Fermi level, and redefine the vacuum, the reference vacuum for us. So one of the things which we looked at before the break was actually this contraction of 2 operators, a creation and annihilation operator, okay, of T2 here. And we found that that one is something which we could rewrite in the following way. So in case T1 was larger than T2, this was given by a delta K of K prime. And then I have an E minus I divided by H bar. And then I have an epsilon K and T1 minus T2. And then to indicate that this is relevant for T1 larger than T2, I can multiply this one with a theta function. So this is T1 minus T2. And I'm looking at the case now when T1 is different from T2. When T1 is equal to T2, this is trivial. And this applies to the case when T1 is larger than T2. So I'm going to redefine this, because later when we introduce Green's functions, this is going to be a handy formalism. So I will redefine this equation here in terms of a function where I now have a delta of K prime. And then I have a function which I call for G of K of T1 minus T2. And this function now contains this exponential, which you see here. So it contains this quantity and the theta function as well. So this applies for the case when T1 is larger than T2. So a particle gets annihilated at T2, and then, gets created at T2, and then gets annihilated at T1. Okay, so this will often be displayed graphically like this. So this specific function G alpha, we are going to display this one as something which looks like this. So we have an arrow, we have a time T2. You can now think of the particle being created at the time T2, a K here, and then a state K, and then the particle gets annihilated at the time T1. So you can think explicitly in terms of time here that something happens at the time T2, and then something happens at the time t1 as well, where in this specific case, the particle gets annihilated. And what we had in this explicit case is that if I have now a dagger, the a dagger k prime with a k, this is obviously equal to 0, because we cannot create a particle at the t1 and then and when t1 is larger than t2. So one of the things which we can also define, if we now have a contraction of, so this is a new example here. So if we have a contraction like this of a time-dependent product of an A of, let's call this K1 dagger, that's T1, and then I have an A of K2 dagger at the time T1. So these are the same times, but we have different K values. So you could now think of the two things being created at the same time. And then this one would be a K3, and this has a T2, and then I have an A K4 at the time T2, and this is multiplied with a vacuum state. So this is something when I now set up the contractions, and I have assumed now that T1 is larger than T2. And then this is something when I set up the contractions now, I have an AK1 dagger, I have a T1, an AK2 dagger of T1, and then I have an A of K3 of T2, an A of K4 of T2. When I'm setting up the contractions now, this is one possibility which I have. And then the other possibility is this one. And then I have the next one. So I'm just using Wick's theorem now. I'm setting up the contractions here. And by the way, let me just not have an explicit time dependence here. No, not to have a specific ordering. So what I'm doing now is simply to use Wick's theorem. And I'm setting up the pair of contractions which I can have. And then I have an A K2 dagger of T1 and an A K3 of T2. So this is just the time-dependent Wick's theorem, which I'm applying. So that means that the other contraction, the other possible contraction has to be this one. And now, if I use these definitions of these operators of G as a function of time, this is something which then becomes equal to this G. And then I have a K1. And this is given by T2 minus T1. So I have to obey causality here. And then I have a G of K2 here. And this is given by T2 minus T1. And then this is again multiplied with a delta, a Kronecker delta of K1, multiplied with a Kronecker delta K3. And then I have a K. So let me just now K4. And this is K2 of K3. And then I have a minus a delta K1 of K3 and a delta of K2, K4. So this is just the application of Wick's time order theorem. And to this specific case, and this G here, the way we defined it, just keep in mind now that T1 is larger than T2. And for this to be the case, then T2 has to be larger than T1, because else this wouldn't make sense. Then we can define particle hole operators like we did before. So if we look at these operators which we defined earlier, so I would have an operator B of K, and this would be a time-dependent operator. And in case this is a particle state, this is given by E of plus I divided by H, and I have an epsilon of K times T multiplied with AK dagger. And then I have an E of minus I of divided by h of epsilon k of t of ak. And this is if k is less than the Fermi level. And this is if k is larger than f. And similarly, I can now define the time-dependent operator here for annihilation in terms of particles and holes. And then I have an E of minus I divided by h bar. And often we skip h bar. If you do quantum field theory, you would put h bar equal to 1. And this is given by A, K. And then what I have then is that this applies to K larger than F. And then I have an E of I divided by H of epsilon K of T of AK dagger for K less than or equal than F. So that gives us now a modification of these contractions. So if I'm looking at a contraction between two operators, I can now set up, or maybe you, okay, let me just change page here. So if I take this B now of K, and then at a T1, and then a B of K prime at a T2, this takes now two possibilities. And this is equal to a delta K of K prime of E of minus I divided by H, and then I have epsilon K of T1 minus T2. So T1 is larger than T2 in this specific case, multiplied with theta of T1 minus T2. And this is given by a delta of K prime. And it's common to indicate this function J here with a larger than symbol. So this is going to indicate that these are particles above the Fermi level. And this is given by this function J of T1 minus T2. And this applies to the case when K and K prime are larger than F. And then I have a next equation, which is a delta of K prime. It's actually not so difficult to see these relations here, plus I of H. And then we have a epsilon K of T1 minus T2. And then I have a theta of T1 minus T2. And that is equal to this delta of K prime. And then I have a G of K. And it's common to indicate it with a less than sign, minus T1, T2. And this is now given in case K and K prime are less than F. And you can represent this graphically in the following way. So I have this G of K larger than of T1 minus T2. That will be given by this graph, which we had earlier. So we have K, and then I have a T1 and a T2. And in this case, K is larger than the Fermi level. And then I have a similar drawing, which I can use now for the state below the Fermi level. So I would have a K here, and then I have a T1 and a T2. So it means that at time T1, we now create a hole, and at the time T2, we destroy a hole. So this is the way we would typically read these diagrammatical or graphical representation of these terms G. You have a T1 minus T2, like that. Yeah.
These are Green's functions to these.
Yes, we are going to relate them to the Green's function and the propagators later. So now I'm just setting up definitions here. And later we're actually going to relate these to Green's functions. So one of the things I wanted to do now, before we move on, is to say something about this adiabatic hypothesis. And how we can relate this time-dependent formalism with a time-independent formalism. Because what we have done now is to introduce this time, or this time evolution operator, U. And we would like to connect this one with standard time-independent perturbation theory. And the reason why we do this is that when we are going to solve the equations for Green's functions, we will be able to sum some terms to infinite order, but at the same time, we will also perform perturbative calculations when we deal with Green's functions as well. So we will calculate something which is called the self-energy to a given order in perturbation theory. And this is used to solve an equation which is called Dyson's equation, which is the basic equation for obtaining the Green's functions for one particle, two particles, etc., etc. So this is another kind of intermediate step and technicality, which we also need in this bigger picture when we are linking what we have done before with perturbation theory, which is fully time independent. So if we look back at what we had earlier, what we had then is that we defined this delta E, the so-called correlation energy, in terms of the exact ground state minus this unperturbed energy. This is when we do perturbation theory. And this quantity here is also a quantity which we have rewritten in different ways. So we have the ground state ansatz. So remember now that this H0 multiplied with phi 0, just to quickly remind you of what these quantities are. So we have assumed that we have, for instance, a Slater determinant, and then we can compute the expectation value of H0, and these Slater determinants are eigenstates for H0. So we could rewrite everything in terms of this interaction piece of the Hamiltonian. So we have the H of I divided by, multiplied with psi 0, and this is in turn given by this normalization factor times psi 0. So this is just another way of rewriting Schrödinger's equation, which we used when we defined many-body perturbation theory. And then we actually used that equations to expand and then obtain the standard time-dependent perturbation theory. So this is just a way to rewrite it. Now, when we now want to link time dependency, linking, because now the state which we are looking at, psi 0, is going to be given by u of t. So this psi 0 is time dependent, starting with a time of t0. And this psi of t0 is normally assumed to be given by this phi of 0. And what we are going to do now is to let this t0 go to time equal minus infinity. So the assumption we are going to make now is that the system does not interact at an infinitely remote time. And then two particles are getting close to each other, and then we get some interactions, and then they go apart from each other, and at the end there is basically no interaction. So the kind of hypothesis which allows us to make the link with time dependence and the time independence and the time dependent formalism is the ansatz now that I can write my Hamiltonian in terms of some H0, which is time independent, plus this H of I, which we had before, multiplied with E and some parameter alpha times T. And the idea now is that we are going to let this as time T goes to minus infinity, then what we have is that E of alpha of T goes to 0. And that means that this H of I term of E alpha of T, that goes to 0 when time goes to minus infinity. So you could think of this as you gradually switching on the interaction. So the two particles are far apart from each other. This is ideal for a type of scattering experiment. So they are far apart from each other, then they start interacting. The wave function evolves from the unperturbed case into an interacting case. And then after some time, the particles get more apart from each other, and then you switch off the interaction. Or we can think of looking at the system at a time t equals 0 when the system is interacting, but that we switch this interaction on gradually. So if we now go back to this time or this interaction pictures we had before, so what we had then was an I of h, and then we had a d dt, and then we had the wave function in the interaction picture of a time t, which was given by the h of I of time t multiplied with psi of I at the time t. So this is the equation of motion in the interaction picture. And now I'm going to simplify life a little bit, so I'm going to put h bar equal to 1, just for simplicity. And what I have then is that this h of I as a function of time is just the exponential of I of h0 times t prime, or times t, sorry, and then multiplied with h, which now is time independent. And this contains now an exponential of this alpha of t multiplied with the exponential of minus I of h0 times t here. So this is the formal definition which we had of the operators in the Schrödinger picture and in the interaction picture. And then what we also had is that when we looked at the solution of the wave function, what we found is that psi of I as a function of t is something which we could rewrite in terms of this operator, t prime, multiplied with psi of I of t prime. So what we are going to look at then is the case when t prime goes to minus infinity. So that means that the kind of solution which I'm looking after is something like this at the time t. Sorry, not that one. Which is equal to u of t of minus infinity. And this is multiplied with psi of I of minus infinity. And this psi of I at minus infinity is the same as our unperturbed solution. And so we have that psi of I of minus infinity is actually equal to this phi 0. So we actually have the ground state which now evolves as a function of time, defined by this time evolution operator. So we can then rewrite psi of I of t equal to u of t of minus infinity multiplied with phi 0. Then what we are going to do then, if we now use the Schrödinger picture, we know that this psi of t is the same as the exponential of I of h0 times t multiplied with the Schrödinger picture solution at time t, like that. And then we also have that psi of I at time 0 is equal to the solution in the Schrödinger picture at time t0, when we just put in time t equals 0. This is something which we discussed partly last week. So that means that for the ground state, what I have now is that this psi of I of 0 is actually equal to psi 0, the exact solution at t equals 0. So you could now think of this as a fully interacting case. So you gradually move on, you switch on the interaction slowly, and then the system starts to interact. And then you have the fully interacting system at time equals 0. So that means that what you have then is that psi 0 is simply going to be equal to u of 0 minus infinity multiplied with phi 0. And when I then go back to the expectation value here, what I have for the correlation energy is that I have phi 0 times h of I multiplied with h of I now has this time piece here, but we put time equal to 0. So we are taking, if we go back here, what we are doing now is that we are taking the limit where alpha goes to 0. So when alpha goes to 0, we are simply left with this term here. Okay? So taking that one, we don't need to have this epsilon. So what we have then is in principle lim alpha goes to 0. So we have an alpha of t, and then this is multiplied with u of 0 minus infinity of phi 0 divided by phi 0, and then I have u of 0 minus infinity of phi 0. So in that limit, what we have then, so let me just leave it here so you can write it down. Yeah, the thing is that, let me just rewrite it on the other page. So what we're getting is actually phi 0, and then I have hi multiplied with u of 0 to minus infinity, and then I have my phi 0, and then I have phi 0 of u of 0 minus infinity multiplied with phi 0. And this last term, which you have here, is actually my correlated wave function of psi 0. So there is a theorem by Gell-Mann and Low, which is partly discussed in the slides, which actually shows that both these two, the denominator and the numerator, they can diverge, but the ratio between them is a constant. It gives a constant expression. And so it's the ratio which actually is the interesting quantity here. Now, the quantity which you also see here, this specific one, or in here, this is what we previously called for the correlated wave function. So the first order term to the energy would just be this one given by 1. And then the second order contribution to the energy would now just be us mixing in 1 particle, 1 hole, and 2 particle, 2 hole states, etc., etc. So this is just another way of writing the correlated wave function in terms of sets of unitary transformations. So the time evolution is just another way of writing the same thing, but then you need to show that these are actually the same things. So the whole thing now, if you look at this expression here, since we are using this adiabatic hypothesis, that requires that this alpha is very small in order for this one to be applicable. And clearly that an obvious solution is that when we take alpha goes to 0, so that the interaction is switched on infinitely slowly. And what we can see then when we are setting up these equations is that order by order in the interaction, this is going to agree with standard Rayleigh-Schrödinger perturbation theory. So this is just another way of expressing Rayleigh-Schrödinger perturbation theory. And let's take a look at that. So the expression here is now assuming that we take this limit where alpha goes to 0. And let's also note, in order to make this link between perturbation theory, Rayleigh-Schrödinger perturbation theory, and this expansion, let's now also just keep in mind, if I take the derivative of dt of this specific quantity of phi 0 of u, and now I'm putting an alpha here because I haven't taken the limit of alpha going to 0, okay? So it means that I'm calculating this still with a parameter alpha. So I have a t of minus infinity of phi 0. This is something which I can rewrite as, obviously, since phi 0 does not depend on time. So this is given by d, dt, and then I have my u of alpha of t minus infinity acting on phi 0. So this u of alpha of t minus infinity, this is something which we are going to take the limit of alpha goes to 0 of u of t of minus infinity. So if we now look at the expressions which we have, if I take the derivative of that specific quantity, so this quantity which we have here, we can actually rewrite that in a particular way. It's actually easy to see that that's the case. So we can take d of dt and then phi 0 of u of this alpha of t minus infinity of phi 0. So if I take the derivative with respect to that, and if we then go back to the expression which we had for the operator, so let me just remind you quickly of that one. If we go back a little bit and look at the expressions which we had for this quantity, you see now if I take the derivative of this quantity with respect to t, that means that what I would have then, when I take the limit from minus infinity to t, I get the h of I here. You see that? So that means that when I take the derivative of this quantity, I would get something which looks like this. So let's go back to the whiteboard here. So this expression becomes then equal to minus I, and then I have my phi 0 of h of I at the time t, multiplied with this u of alpha, which now has this dependence on alpha in the expression for the interaction piece, multiplied with phi 0. And that means, if you now look a little bit closer at it, is that I can set up d of log of dt of this quantity, phi 0, and then u alpha of t minus infinity of phi 0. This is the same as minus I, and then I have my phi 0 of h of I of t multiplied with u of alpha of t minus infinity multiplied with phi 0. And this is divided by phi 0 of u of alpha of t minus infinity of phi 0. And we know also then that if I take h of I at time t0, that is just the same as my original h of I. So what I can do now is actually with this expression, if you look a little bit closer at what we had earlier, so I can actually set up delta E as the limit of alpha goes to 0. And this is given by an I multiplied with a d dt. And then I have log of phi 0 of u alpha of t minus infinity phi 0. And that's just end of parenthesis here. And this is taken then at, oh, maybe you don't see that properly because it doesn't. No, yes, you can see it, yeah. And this is obviously taken at t equals 0. So what we can do next now is to link this expression with many-body perturbation theory and time-dependent many-body perturbation theory. So the question is, can we link this with time-independent, and then we have Rayleigh-Schrödinger perturbation theory. So let's at least show it to first order. The second order, you have some more involved calculations, but this is just a small digression. So if I look at this operator, u, the time evolution operator, minus infinity, we can write this out as a 1 plus a series of terms where I simply sum from n equal 1 to infinity, and then I have a u of n here. And this u of n is now, if I go back to the definition of this operator u, this time evolution operator, this is nothing but an integral series of integrals from minus infinity to time t, and then I have an hi of t1 dt1. There is a new integral from minus infinity to a time t1, and then I have my hi. So this is my time-ordered usage of Wick's theorem on this specific quantity. So I have a minus infinity up to a tn minus 1, and then I have an h of I of t of n of dt of n. So if I now take this series here, if I now look at the expression, so this is nothing but just me using the time ordering through Wick's theorem, and I would have a phi 0, and then I have a u of alpha of t minus infinity of phi 0. If I look at that expression, this is something which I can rewrite in a more compact term. And then what I'm going to do now is to recognize each of these terms in this expansion for a given value of n with different orders of many-body perturbation theory. So if I now rewrite this, I can rewrite it in terms of a phi 0 over 1 plus a sum over n equal 1 to infinity of this u of n acting on phi 0. So this looks very much like what we have seen before. And then we have this one as a 1 plus a set of terms, n equals 1 to infinity, and this is a of n. And this a of n is nothing but our phi 0 of u of n with phi 0. And that looks very much like our correlation operator. So this is just a rewrite with time here of the so-called wave function operator or correlation operator, as we called it earlier. So what we can do next then, if we take the log of this quantity, so we take the log of the phi 0, and this is where we will stop today, and we will pick up this tomorrow, of alpha of t minus infinity of phi 0. This is the same as log of 1 plus this term n of a of n. And now we can Taylor expand this. So when we Taylor expand it, it's going to give us an n of a of n minus 1/2 of a sum a of n squared. And then I have plus, and I think this is 1/3. And then I have a sum a of n cubed, and this goes on to infinite order. Now, there is a very important thing here. In order for this to be true, this a of n has to be larger than -1 and smaller than 1. And that means that every term here has to be treated really as a perturbation. And if not, this Taylor expansion or the log will obviously not be possible. So let's stop here now. And then tomorrow, I'm going to reorder this sequence. And we are going to see that we can then reproduce Rayleigh-Schrödinger perturbation theory order by order. But we won't go beyond second order, because when we do third order, this is an exercise for those of you who have lots of spare time. But you can actually show this order by order. When you take the limit, when this alpha goes to 0, and you set t equal to 0. So you have a clear connection between Rayleigh-Schrödinger perturbation theory and this interaction picture time evolution operator acting on the ground state. So the whole thing is that this is just another way of rewriting the correlation operator, but now with time. And for us, this machinery is going to serve the purpose of linking with Green's functions. That's the main reason why we do this, because else we could have done everything here if we just stopped with many-body perturbation theory and went to copper cluster theory, we could have left time out of the picture totally. But since we are linking this with Green's functions, we need to introduce time. And so tomorrow, I wanted just to end this piece, and I will say something of Gell-Mann and Lowe's theorem. And after that, we are going to dive into the definition of Green's functions and the actual equations which are used to find the Green's functions. And one of these equations is going to be Dyson's equations, which is one of the standard recipes which are being used in Green's function many-body theories. So we would just scratch the surface, unfortunately, because the semester is going to end next week. So I just wanted to give you a kind of feeling of what is the link between standard time, the independent theories, which we have dealt with basically till last week, and the time-dependent formalism, because that also gives you a link with the quantum field theory.